All right. Good morning. Good afternoon. Already my last lecture, so I need to say everything I still want to say. And we ended yesterday with a kind of a cliffhanger. I announced the quasi-adiabatic evolution introduced by Matt Hastings, and we will get to it in a minute. Because this will bring us back to the sort of the theme of this conference about gap phases. And so I'll introduce a definition, and then I will explain everything we've introduced about dynamics, how it can be used to construct that quasi-adiabatic evolution, and how it plays a role in the study of gap phases. So remember, we introduced the class of decay functions. Not that these exact formulas have much relevance if you don't do the estimates, don't do the proofs. But just to give you an idea, if the parameter A and theta appear, then you'll know what it means. Then there will be classes of interactions P in something like B A theta. And phi could also be actually a function of some parameter, phi at time, usually, maybe of an interval, maybe one, a differentiable one, specifies some decay. Again, the exact definitions of the norms that define these bounded spaces of interactions are motivated by what you have to do to prove the statement. So it won't be entirely apparent from just a statement of the theorems, but to state the theorems, I have to kind of say what the range of applicability is. Okay, so let's define gap phase in the context of quantum spin systems. So behind all of this, there is our discrete metric space and our algebra of quasi-local observables and the other algebras of local observables that we have introduced. And we are looking at ground states, particular gap ground states. And so the question of this whole conference is how can you classify the entangled states that make up the ground states of a whole family of models. There are different phases to be distinguished, maybe distinguished by invariants, topological invariants of some kind. And I think the first sort of technical definition that I'm aware of was given by Chen, Ku, and Wen in 2010. There was more than one paper ultimately. And in the language that we have introduced here, we would consider, say, two interactions, T0 and T1 in one of these classes. I jumped ahead. Say BA theta, and I could actually leave the parameters open, but I'm going to have my theta strictly positive and my A strictly positive for the discussion. So some A positive, theta positive. And suppose that they have gap ground states. Let's call them omega 0 and omega 1. It could also be sets of ground states. I mean, it's not necessary, this is not restricted really to the situation where you need gap ground states, but it's sort of slightly simpler to formulate it if it's just have one state. So we could also consider sets of ground states, SE0, say, and SE1. And so the question is when these, you know that these are both, say, interactions with a unique gap ground state. When would we say that they are in the same phase? Then the first definition, maybe I'll put the two definitions here in parallel. So that is Chen rule 1, 2010. We define an equivalence relation. Phi0 is equivalent to Phi1 if you can interpolate, and to make it a theorem with interesting consequences, I'm going to say if there exists a Phi1 curve of interactions, this Phi in B prime for some A prime theta prime of 0, 1, such that, well, first of all, it's an interpolating curve, so it begins at Phi0, it ends at Phi1. Yes? A dot. Yeah, I have various, depending, sometimes it's time, sometimes it's a parameter. I will have actually a few different notations for this function, but here I just think of it as a parameter dependent interaction. Parameter S that lets me interpolate between Phi0 and Phi1. And I introduced a norm that involves also the derivative. It's basically an F norm of the interaction plus an F norm of the derivative of the interaction. And actually also multiplied with the support. We want to have a little bit more decay for the derivative than for the interaction itself. And that's sort of a technical detail. To have a curve of interactions.
Sorry, excuse me.
Yes.
The indices of the family B prime A comma, are they the same? I mean, as
No,
you would...
not necessarily.
Okay, they are okay. Interesting.
I would not require that.
All right.
So, and I really mean this these definition to apply to any A positive, theta positive. The interactions may be given you with some knowledge about how much decay they have, but no, the curve may needs to have decay also, but it doesn't have to be the same values. And then number two, it's uniformly gapped. So there is a positive gamma such that if you fix this S, this gamma is a lower bound for the ground state of the ground states of the interaction phi S for all S in 0, 1. So along the curve, there is a strictly positive lower bound for the gap. Now that this can be slightly modified and relaxed, and you don't really need C1, the derivative could be piecewise continuous or something like this, or even just bounded and measurable, it would also work. But for concreteness, and because I'm sort of state a simple theorem, we will adopt this. And so this is it's not so difficult to prove. It's easy to see this is an equivalence relation. If you concatenate curves, then you may have to modify them a little bit to make it differentiable and so on. But this is all kind of minor details, easy things to do. You can check. This is an equivalence relation, and that's what Chen, Gu, and Wen meant when they talked about uniformly gapped curves of Hamiltonians. Okay, so it's been mentioned. Yes.
Why not just have continuous curves?
Because I will want to prove you could definitely define an equivalence relation with continuous curves. And it would be perfectly fine as an equivalence relation. But I want to prove certain things, and in particular, that it implies definition 2, and for that I have to make a construction that involves the derivative of the interaction. And the derivative could be a weak derivative, or, I mean, you could definitely relax this definition. So there's not intrinsically something physical about this differentiability here, but it's mathematically convenient to have. So the second one doesn't talk about interaction.
To say
Yes?
there was a question that appeared in the Q&A. I don't know what it is, but it appeared there.
Most of the useful things are differentiable. All right, this is for the philosophy. Yeah. Okay. So this is equivalence of interactions. But if you want Hamiltonians, that's certainly one very common way to talk about this, but you can also emphasize states, equivalence of states, which you think of should be gap ground states of some interaction, but you sort of don't emphasize the interaction. And again, it could be your sets of states. Useful to consider sets of pure states, in fact. And so let me write it for states. Omega 0 is equivalent to omega 1. If there exists, I'm going to write it with an interaction, but it's just to specify a family of automorphisms that have nice properties, and I want these automorphisms to be generated by an interaction with sufficient decay. So it will preserve locality. There would be other ways to formulate it, but it's sort of a direct way to do it. So if there exists some A and theta, because I want to work in a class, and it's C, a parameter dependent interaction from 0, 1 to the interactions such that two properties are satisfied. So first of all, here I would assume that this function is piecewise continuous. It's also more than I need. But it's sort of a convenient class to work with in the norm of this Banach space of interactions. And then two, so the automorphisms alpha S generated by C. So now this S is not a parameter. I consider to play the role of time in the differential equation of defining dynamics. It's of course not a real time, but I solve the differential equation of the dynamics from time equals 0 to time equals 1 using this time-dependent interaction psi of S. I get a family of automorphisms, alpha S, and they will satisfy the Robinson bounds and all of that because that's true in general. And what they do is interpolate the states in the sense that one. So if I go from 0 to 1, of course I could just say there is one set automorphism, but I'd like to have it generated in this way. And so if you want, you can forget about the other ones. But I like to think of it in this way, and I can if I have sets of pure states, then I would want one automorphism that maps all the states from one set in the states of the other set. Okay. So these are sort of two definitions. And so the next thing I want to say is to show you how they are closely related. Yes.
This is like continuous. Obviously, it's different.
Continuous. So I don't need to take the derivative of this interaction. But the derivative of this interaction, so to speak, will be used to define the psi, and then the psi generates the alpha.
So the psi can jump finitely many.
Yes, yes. These automorphisms that you get by that are generated by the interactions, they are actually depend continuously on the norm, but also with a factor of time. So you can easily see that when you solve the dynamics, even if the psi has a jump, alpha will not have jump. The right hand side of the differential equation doesn't have to be continuous. It's going to be bounded and nice enough. Otherwise, you will have a nice solution.
Great question. So I'm sure confused. How does alpha sub s, like, it has only one index, but it seems like you like the auto.
Yes, right. So this is this family, if you want, alpha S0. But in fact, I'm really using only alpha 1, just sort of explaining how I got it.
And the S is the one that corresponds to the input to psi, is that correct?
Yeah, so the S plays the role of time, and this psi. No, there's yeah. I will make the connection with phi later. The interaction that generates alpha here is called psi.
Yeah.
And maybe I'm making it slightly confusing by taking it dependent on the parameter. I could have first talked about one automorphism, but it's kind of convenient to have sort of the continuity.
This is good, thank you.
Yeah. Okay. So now I can explain what the role is of this Hastings interaction that I put on the board yesterday. So I'm not going to give sort of a full discussion. But basically, what is the case is that so here we don't say that these states are ground states, but in fact, if you have this, and one of them is a ground state of a gap ground state of an interaction, then in fact the other one will be, and there will be a curve, and it will also satisfy this definition. This you can see using the quasi-adiabatic evolution of Hastings, which we will also need for another important result. So it's worth going through. Let's see, how am I doing here? Okay. All right. So for simplicity of the presentation and sort of, I'm going to assume that my interactions now are supported on balls, so that I have few parameters to take care of. So we will sort of a working assumption. It's not a restriction, and the very big conditions. The only non-zero terms are labeled by centers and radii of balls, and I'm going to assume that maybe I can also simplify the notation and call this Px of Pxn, and the norm of Pxn is bounded by some of these functions g of n. Maybe it's a slightly different function. And if I have a parameter dependent interaction, then I can put that variable there. So what I introduced yesterday was a transformation So if I have my phi of s here, this is phi of s, but it's here. So I denote that I fix s. I get an interaction phi of s, and so this is generated with a time independent interaction, and I apply it to the derivative of these terms of my parameter dependent interaction. And then integrate against the weight function, and this W of T is an L1 function of rapid decay, and the parameter alpha, it's really a scaling. So W alpha T is what is it? I think the scaling is 1 over alpha W1 alpha T, something like that, for some positive alpha. And it decays as some constant e to the minus a absolute value t, with a log of a absolute value t all squared for large t. So it doesn't decay exponentially. It does decay faster than any stretch exponential though. And this will be important. That's why these stretch exponentials sort of come in naturally. I mean, you could do something else, but so this is going to be well defined because oh, I did not introduce phi of x yet. So I'm going to this phi of xn, phi of xs is the sum over n of the phi xn's. And because they decay rapidly, this converges absolutely to some bounded thing with rapid decay, well localized. I'm going to time evolve it. These interactions are also fast decaying, so I have any problems in bound. So this will be well localized in time. For a fixed time, they will be well localized in space. This function here is a function of rapid decay also. So clearly that's well defined. And I think it won't surprise you that this is somehow also a spatially localized element of the quasi-local algebra. But it's not an interaction because it's not a local element. No chance it's a local element. But what I can do is write it as a sum of local elements, like it's what happens with interactions. So let me explain that now. Maybe I'll do this here.
So I'm confused about indices. So does phi xn also depend on s? That is time. Right?
Yes. There's also this is s by s. Yeah.
And what is the standard in integrand is tau upper phi?
Yeah. So I didn't use the notation before. We were just talking about the interaction. I consider the dynamics of the interaction phi as instantaneous. So s is a fixed parameter here. It's a time-independent interaction, generates the dynamics, and I apply it to this particular algorithm. And then I do this weighted integral. Okay. Yes.
I don't quite understand what you're doing. Are you putting in the W as like you're taking any W that has this property?
No, it's a particular W. Specific.
Okay.
Well, it's not quite. I mean, there's a whole bunch of freedom in the W's also, but you try to. So this is discussed in one of the references that I posted, our long JMP papers, 2019. How to construct good functions with as much decay as you can master that satisfy some other properties. The derivative of W has to have Fourier transform of compact support and so on. So there's a number of conditions. It would take too much time to tell you explicitly how you can construct this function.
But for now, it's any function.
But yes, this is an L1 function. This is well defined. But it wouldn't necessarily have particular interesting properties. And if the L1 function has a lot of decay, then that will be good for the decay of the interaction psi tilde that I'm defining now. So at the moment, there is nothing else. But I'll come to that in a second.
There was something in the Q&A. I don't know what it is.
Well, let me update here. The star is interpreted as the Heisenberg picture or image. Well, yes, if it's the Heisenberg dynamics applied to this observer. Does that answer the question? Okay.
The person probably responded, or there's something in there.
Okay, it's probably not very productive for me to answer here.
I'm just looking at the screen. I just see the thing pop up at the bottom.
Okay. So Daniel, maybe you can do the answers in the Q&A. That would be great. And then we can discuss later. I'm happy to answer questions later. Okay. So this is now local, so I have to do some transformations, and I'm going to use these conditional expectations to do that. So I'm going to use my conditional expectations in Bxn. So this suggests that it is localized around x. And what I'm going to do is I'm going to define a psi x1 of s, which is 5 dx1 of psi tilde of this psi tilde xs. Then c xn for n greater than 2 is going to be 5 b xn of this psi tilde xs minus the previous one. So what I'm doing is cutting out the interaction. So I have, if I sum all of these up, I have a telescopic sum. Okay, I add the second term to the first term, this cancels, and I have bx2 of this, the conditioning on the complement of 2, and then the radius of the ball of radius 3, 4, 5, and so on. And so the sum, I'm going to define so this psi, what was it? Psi tilde x n that I defined there of s, I can now write as a sum over n of this psi x n s's, which are in the algebra of Bxn. Just to, because I want to work with the local terms that make up the interaction if I want to prove properties of these automorphisms generated by psi, which is what I'm going to do. Okay, so this is a transformation that gives me an interaction associated with every differentiable curve of interactions. Right? And I can apply that in particular to these curves that supposedly interpolate between two interactions that are in the same phase, same gap phase. Okay, we're not there yet.
Why is there an
Good, thank you. Okay, so I will maybe formulate the theorem and then maybe make some comments. I mean, time goes fast, so let's see whether maybe I'll just let's see this. So we can do a quick erase. So here is the theorem. So suppose P0 is equivalent to phi1 according to our definition with a interpolating curve that is this phi of S. Some nice differentiable interaction with sufficient decay. With a gap that is bounded below by this positive gamma. Then the alpha S, or if you want, alpha S0 generated by, I should have given it the name, I mentioned it. So this is what I'm going to refer to as the Hastings interaction. So that is this side, this curve psi of S, where the parameter is interpreted as time. And it's not explicit in the notation, but with alpha chosen to be the way it's defined. If you would refer to the paper where we construct these functions, and of course it's a little bit arbitrary, but you have to take alpha small enough with respect to the gap that is the uniform bound for the gaps. The respective parameter gamma, that's a uniform local bound for the gaps of the interpolated curve. And the way they are sort of defined, that there's this coefficient, which of course I could absorb. The optimal constant, I don't think can be determined. I certainly don't know it. But the point is that you choose a positive alpha that is small enough with respect to the gap. Was it alpha or A? It was A. So I cannot get arbitrary fast decay. It's sort of determined by the gap that I have, how much decay I can have. And then, I get that this is automorphisms that map the ground states along this curve into each other. Now, but the way I've defined it, I believe, is the other way around. Omega 0 composed with alpha. That's 0. That means 0, 1. Where this omega S is a gapped ground state of phi of S.
For suitable choice of W.
Yeah, so the W that I didn't really explain in detail what it is, but if you take one of the ones that satisfies the right conditions, and here I said it's a specific one, you have to go look in the paper what it is, but it has a parameter in it. You have to choose that parameter small enough, then it will satisfy this. So what's the role of this parameter? It guarantees that this interaction that is generated there will be such that it adiabatically follows the ground state that is separated from a gap from the rest of the spectrum. So when the dynamics goes, it has these terms that mixes the different parts of the Hilbert space. But in fact, the two parts of the Hilbert space that are separated by this gap, which is at least gamma, will not be mixed if you choose this function correctly.
Actually, alpha, not H. Sorry.
Is it?
Call it alpha.
Do I? Yes, but I should call it A because I have an alpha. I don't want to confuse it.
You also have an A.
Yeah. You know, we all speak Greek, so. So with alpha is the automorphism, A is this parameter.
But the other A is not missing, right? Now there's two A's in the same one.
Yes, I see. Okay. So it's all A's here. The parameter is A.
But also A in the definition of the decay function.
Yes, very bad, very bad. No relation. No relation. This is too much to change. Yes, different name. I'm sorry about that. I should have caught that.
This is the second index of alpha. Alpha is the S0. What is the 0?
Well, so I mean, first I didn't put the 0, and then someone asked why there's no 0. So this is not a group of automorphisms. It's really generated with the time-dependent dynamics, where S plays the role of time, and so it's the evolution from 0 to S generated by that time-dependent interaction. You could invent better notation. You can put everything in the notation if you want. So, but
Thanks.
that's what it is. Okay. So what this choice of decay function guarantees by it relates to the support of the Fourier transform of the derivative, is that the interaction doesn't make jumps of that are larger than the gaps, and so it can mix up all parts of the Hilbert space, but it cannot bridge that gap that separates the excited states from the ground states. Maybe there's more to say about that, but this will have to do for now. Okay. So this is then clear that at least I have sort of an implication from definition 1 to definition 2. I'm not going to talk much more about this. You can also kind of see that if one of the states along this curve, or if omega 1 or omega 0 are actually the ground state of a gap interaction, then this automorphism will actually generate the curve of interaction. That automorphism alpha that I use to define equivalence can also be used to generate a curve. Okay, so this is definition of gap phases. At first, so for a while, people were applied this definition also. I mean, they wanted to figure out first in one dimension and then higher dimension what the different possible topological phases would be. Figured out pretty quickly that in one dimension, yes. Yes. Well, okay. So no, it is actually a very good question. So if the original phi has a symmetry, if this curve has a symmetry, for all phi s is translation invariant, or maybe it's local gauge invariance, or a discrete symmetry, or time reversal symmetry, or charge conjugation symmetry, or whatever, it will transfer to the interaction C. So it will have the same symmetry. So there's no symmetry requirement here. But if I do have symmetry, this quasi-adiabatic evolution, this Hastings generator will have the same inherent symmetries of the curve of interaction. And that's important when you study SPT phases. So I've defined this without making any symmetry assumptions. In one dimension, this sort of gave us a way to prove in the end that in one dimension there is no interesting topological. There's only one phase, so to speak. This changes when you impose a symmetry. You get a symmetry protected phases. And you can use the same definition, and the only thing you have to modify is that the curves that you allow for every S have the symmetries that you want to protect. And that often includes translation invariance and maybe some additional symmetries. Okay, I will show some examples soon. And so it's important that, and you have to sometimes work a little bit to see that. So it's there's a specific good choice of functions. Like for instance, if you want to conserve time reversal symmetry or charge conjugation symmetry or something like that, you need to choose this function that is odd in T and real valued and so on. But there is a way to do it that all the symmetries are present in the resulting C. Does that answer the question? I think it answered the first part of the question. I don't know what the rest refers to, but we can talk offline maybe.
Just motivational part.
Yeah. Okay. So, but now that we have an interesting classification problem, and we can do this for all kinds of systems and with all kinds of symmetries, added symmetries, if we like, and study SPT phases or other topological orders. But it would be interesting to know that there is actually a good supply of interactions with gap ground states, that it's not some anomalous situation, that if you have a gap state, that it actually is connected by a curve to another gap state. And this is the question of stability of the spectral gap. And so I will mention one result along those lines now. I think I can use this. We need these definitions up there a little bit. So it takes a little bit of time to formulate the result, and so I will try to do that and sort of explain what the conditions are. We don't have a very general result. For the moment, the only kind of general gap stability result that we have is restricted to assuming that the unperturbed model, the one that we want to be stable, is finite range frustration-free interaction. Okay, so but there's a recent version that is kind of interesting, I think. I will call it bulk spectral gap stability. That's joint work with Simps and Young, letters in mathematical physics last year. So, but it is restricted to frustration-free finite range interactions. So what I mean by bulk spectral gap there, which is kind of interesting that when people talk about locally gapped, something, but sort of typically they mean exactly the same as what I mean by a bulk gap. So when we defined a gap system by going to the GNS representation, so I take the thermodynamic limit, I look at infinite systems, then sort of the first thing that comes to mind, maybe you have something, a system defined on Z nu, you have all of Z nu, and everything you say about it are properties of the bulk in the sense that there is no boundary in view. But you could also take the thermodynamic limit over half spaces, and you get, say, Z nu restricted to first coordinate being non-negative. Then you are actually studying the edge, and you can do all the same things, and you can ask whether the GNS Hamiltonian for the ground state on a half space is gapped or not. The answer doesn't have to be the same. And in fact, in some cases, we know, interesting cases, you have a very robust set of edge expectations that are gapless, continuous spectrum, right? And these two can go together. And this poses a problem if you think about the question of gap stability. So what we're going to do now is consider families of models. So the finite volume Hamiltonians, which are well defined as Hamiltonians, are going to be of the following form. So it's going to be a family that I consider as being perturbations of a finite range frustration-free model. So I'm going to assume that this is something like the toric code model or the AKLT chain or something like that. So this is going to be finite range, maybe translation invariant, not necessarily positive, and there is a zero energy ground state. And then I'm going to add something more general with a constant S in front that I can limit to be not too large. And maybe I perturb it in some volume lambda with some phi, some interaction. I'm going to assume it's supported on all. So I'm going to consider a family of models like this, but this is the perturbation of this frustration-free model. And so then, if I want to, so what I want to prove is that if this model for s equals 0 has a gap, then for small values of s, it also is gapped. For some general class of perturbations and under some assumptions. And so, but if I have a situation like I just described, where I have a model maybe defined on a half space, and it sort of for specific topological reasons, it needs to have gapless excitations on the boundary. Then I would be trying to do perturbation theory for a gap, and so it's stable, but actually the Hamiltonian that I'm starting from doesn't really have a gap in the spectrum. So what I need to do is go to the representation of the bulk, which is the GNS representation, say, on full of G nu, where the GNS Hamiltonian has a gap, the edge modes have disappeared, and I can do perturbation theory then. Now, of course, there are situations where I can do this in different ways. Put periodic boundary conditions, sometimes that works, but maybe I have a quasi-crystal or something like this, and periodic boundary conditions don't make sense. So I want to do this in the GNS representation and perturb the GNS Hamiltonian and see that its gap is stable under the perturbations of this type. So we need some assumptions for this to work. And it's kind of a long list. So maybe I will try to abbreviate a little bit. They're not really restrictive. So I have some gamma d, and I'm going to have to assume a number of things. So for instance, Z nu works very well, but there's many other things that work. So I already mentioned the condition of nu regularity. Points don't bunch up too much. Size of ball is bounded by a power. There's another assumption that I need, which I'll just describe in words. It's the existence of separating partitions, which means that for every n, I should be able to color the sides of the lattice with no more than polynomially n colors, so that all 2 points with the same color at least distance n apart. You can write this out in mathematics. It's obviously true for Zn. You can figure out a coloring of points, but that's a condition that we use. So the second thing is that so this H is Hx that is finite range. So there is some constant R such that Hx is in the algebra of the ball of radius R centered at X for all X. Then I will have the frustration freeness. So there exists an omega 0 of my system such that omega 0 Hx vanishes. I have uniform boundedness. So the sup over X in gamma, the norm of Hx, it's finite. So these are kind of very innocent conditions that you expect. Number 5 also, well, we have to start from a gapped system. So this is the positive gamma 0 such that the spectrum of the GNS Hamiltonian is contained in 0 gamma 0 union interval gamma 0 infinity. So these are not very restrictive functions at all. So the next one is certainly also satisfied in many examples. Is the one that allows for gapless excitations at edges. So there's a constant C and Q such that if I take these finite volume Hamiltonians, let's take balls. I can generalize this too, but the unperturbed model. Now look at the gap of that. It may vanish, but not too quickly as the radius of the ball increases. Only as power, any power will do. So typically, that's what you have when you have edge modes. Then there are some conditions on the perturbation. So this phi there that I have, phi of dx and a norm has to decay as some stretched exponential, and I have my A again. Maybe I should use B. Some B positive, state of positive. Then I keep the most important thing for last. I need to have LTQ. Local, topological, quantum order. Not sure why I write it out, because the words don't really explain very much what it is, but let me tell you with a formula. So let P lambda be the orthogonal projection onto the kernel of the unperturbed model on lambda. I'm going to use it for both. So this is about this finite range crystallization free model. There's a bunch of zero energy states and finite volume. It could be unique. It could be exponentially many. We saw the example of the toric code. Depending on the boundary conditions, depending on how you define it, you may have an exponentially growing number of zero energy states, but there has to exist a decay function. I'm going to call it capital G, such that for all A and some finite ball, and I will put the rest of it on the next board. I think I have it over here. That's clean. It's not clean. Machine is bothering us. Okay. So I have this projection, and in terms of that, I have the following kind of estimate. If I take a local observable A, so this is for any x and for any k, and I project it between the ground state in the ball, what's my notation, dxm, dxm, and I compare with just the expectation of A times this projection. This is upper bounded by norm A, then something that's important depending on the regularity times G of m minus k. With something else. So this G is not arbitrary. Of course, this is always bounded. I want it to decay, and I want it to decay fast enough because I want my G in the right-hand side to have a moment, a finite moment of a certain order. which is related to the vanishing of the edge modes and the dimension or the regularity of the directions. So actually, the finest condition is with the square root of G satisfying this moment condition. So these are 8 assumptions. I make sure I can show them all at once. No, I won't succeed. This one is what's different now. I don't know. Not easy to see the whole thing, I guess. All right, so that's the conditions. So it's a pretty broad class of systems. So then here is the theorem. So assume 1 to 8. Then for what did I call the gap? Gamma 0. So for all gamma positive, but less than gamma 0, exists another constant beta, such that for all S, bounded by an absolute value by gamma 0 minus gamma over beta gamma 0. There is a ground state omega S of the system defined by the perturbed local Hamiltonians. So this has 2 pieces in the action. That's why I write it like this, with the gap of the GNS Hamiltonian omega S bounded below by gamma. And in fact, this omega S will be connected to omega 0 by the Hastings adiabatic automorphism alpha S, constructed by considering this this system where I now have so I consider this as a curve of interactions, and I look at the Hastings evolution generated by it. So the derivative is just now phi. I use this phi to create a Hastings generator. Then I get alpha, the quasi-adiabatic evolution, will produce the ground states of the perturbed model, and I will have an estimate for the gap. But it's 3 o'clock. And so I will leave it at the statement and maybe just show you an application. I have 2 slides to show you that in 30 seconds or 1 minute, maybe a few minutes. So I hope that this is sort of clear. It sort of shows that if there's something you have to choose, how far you want to go, but the gap doesn't close more than linearly in the parameter S. So this is, of course, an unbounded perturbation. If you go to the infinite system, this is an unbounded perturbation. This is not bounded perturbation theory. But what you can prove is that under the conditions that I have stated, this becomes a relatively bounded perturbation for some unitarily equivalent Hamiltonian. Okay, so let's go to the full screen. Okay. All right. So you have to stop. So here is a generalization of the AKLT chain to n-dimensional spins. So if n is equal to 3, I'm talking about the AKLT chain. I don't know whether you remember the interaction that I put on the board at the beginning, which are spin 1 chain, the 3-dimensional spins. So it turns out that you can write this as a little combination of 2 operators on nearest neighbors, and one is the swap operator. That's the Tx plus 1. It swaps the state on these 2 tensor factors, and then the other one is the rank 1 projection on the maximally entangled state. And if you generalize this to n-dimensional spins, and you consider nearest neighbor interactions of the form ut plus vq, if t is the same, q is the maximally entangled state, is a projection on a maximally entangled state C with respect to some basis. And then you can use 2 real coefficients, u and v, to have an interesting class of interactions. You get a family of models which has been special cases have been studied a long time. It was looked at as a family by Tu and Zhang in 2008. And you find a pretty interesting phase diagram. Can I advance? No, I cannot advance. Okay, escape. Oh. This is not, here it is. So there is a parameter u and v. The magnitude really doesn't matter very much. The ratio, their sign matters. You get a phase diagram, you can plot on a circle. You can assume u squared plus v squared is equal to 1, say. And you find that this spin chain likely has 4 phases. Not everything about the phase diagram has been proved, but quite a few things are. And there is 2 gapless phases and 2 gap phases. But depending on these parameters, you get a ferromagnetic ground state and gapless excitations. You get a phase that has some interesting incommensurate spiral correlation functions that, however, are powerful, and there's gapless excitations. And then there's 2 gap phases. There's the yellow one, where you have breaking of translation invariants and dimerization. And there is the red one, which generalizes the Haldane phase of the AKLT chain. And it has a special point in there at v equal -2u, where the model is frustration free and the ground states are given by matrix product states. There's a lot one can say about, it has been studied a lot, there's a lot one can say. Many papers are just about one particular point in the phase diagram. But one question that was open until recently is what happens for larger values of the spin dimension and in this red phase. So for n equal 3, it has a unique gap ground state and it's a non-trivial SPT phase. For instance, all this technology we have introduced can be helpful, and Ogata generally defines her index. It in fact goes back to Pullman, Berg, Turner, and Ishikawa. Determined that there is this H2 index that clearly shows that this, under various kind of possible choices of symmetry protection, this red phase is non-trivial. You cannot connect to a product state without closing the gap if you preserve a little bit of symmetry, translation variance, and a little bit of rotation symmetry or some discrete symmetry. Now, what happens for larger values of n now depends on the parity. For odd n, you find exactly the same type of behavior, n equal 5, 7, and so on. You have unique gap ground state that is in the Haldane phase. There's a non-trivial SPT phase. We can prove that in various ways. My student, Michael Rigoni, wrote his dissertation. He graduated last year with a dissertation about this model. You can read in his dissertations on the archive. You can read about it there in great detail. And for even n, as it turns out, the translation variance is also broken, like it is in the yellow phase. So dimerization is when translation variance breaks in a way where nearest neighbor pairs become strongly entangled with one other neighbor. So everyone chooses a neighbor to be strongly entangled with, and there's 2 ways of doing that to cover the lattice. That's why translation variance breaks. And so you might think that for even n, something similar is responsible for the breaking of translation invariance in the red phase. But in fact, this is not at all the case. Because, for instance, there is this model has ON symmetry, generalizing O3 symmetry of the KKLT model. And what happens for even n is that this ON symmetry breaks down to SON. So the reflections with determinant -1 are broken in the red phase for even n. While the yellow phase has, in fact, all the full ON symmetry for all states. Only translation invariance is broken. So by that alone, that you know that these are different phases, because of the theorem. If you combine the theorems that I just mentioned, the definition of equivalence and the curve and the existence of the automorphisms that map ground states to ground states when the gap doesn't close, while preserving the symmetry, tells you that it's not possible that there is a gap all the way from the red to the yellow phase. There has to be a phase transition. There's many other interesting things to say about this, but time's up, and I will stop here. The story isn't finished, but that's good. In summer school, the story shouldn't be finished because it's up to you to add to it. Now, there's obviously a lot of open questions and a lot remains to be done. So I don't have a grand conclusion. I will just stop here. Thank you very much.